first of all, what does that symbol mean? Yeah, it's the greatest integer function. Do we have any limit laws concerning the greatest integer function? No. Kind of like absolute value. We don't have anything that says we can just do the limit of the inside, so we have to use a different approach. So we could either make a table of values or think about a graph. Let's think about a graph. Do you guys remember what the greatest integer function looks like? It tells us that
Is
you
the line, line.
Yeah. You can only get out integers. So if you put in 0, 0 is an integer, you get 0 out. Okay, if you put in 1, 1 is an integer, you get out 1. But the weird thing about this graph is what happens between those. So if I put in 1/2, 1/2 is not an integer. The greatest integer, you can't get out anything bigger than what you put in. So you have to give me the closest integer that's not bigger than 1/2. So you would still get out 0. If I put in 3/4, I still get out 0. If I put in 0.9, I get 0, or 0.999, or 0.9999999. So to show that we're on this step all the way until 1, we put an open circle here. And so then you would stay on this step until you put in 2. So it would go from up to 2 with an open circle, and then 2, 2 is your closed circle. Okay, and you'd stay on that one until you got to 3. And then if you put in 3, you get out 3. So it was our step function. We are approaching 3 here. So here's when x is 3. Can you tell me what the limit is? If I'm approaching from the right, I'm getting out 3. If I'm approaching from the left, what am I getting out? 2. So they don't match. What does that mean about my overall limit? All right, so for anything that doesn't follow our limit laws, we have to go back to either a table or a graph to figure it out.
So then would all greatest integer things does not exist?
If I give you an integer. But if I said the limit as x approaches 2.5. So if you're approaching 2.5, here you're getting out 2, and from there you're getting out 2. So that one would work. So the integer values, it doesn't exist, but decimal values it would. Good question. Any other questions there? All right, final thing that we need to talk about in here. Sometimes we have functions where we just can't evaluate the limit using limit laws, and they're pretty complex, so graphs can be complicated, tables can be confusing. There is one other option, it's called a squeeze theorem. And it says, if one function is smaller than the other, its limit would always be small, okay? Which should kind of intuitively make sense. If I have two functions, function f is up here, function g is down here, can you agree that no matter where you're at, the limit of f, I flipped it, pretend like this is g. The limit of f is smaller than the limit of g? Yeah. Well, that's also true if it's between two things. So if g is between f and h, its limit would have to be between the limit of f and the limit of h. We are really only going to do these in one specific example. I'm going to show you some cases with trig functions. We aren't going to do a lot of them, so we'll do a couple. You might have a couple on your homework test or quiz, maybe one question. Okay, it's not going to be something we do a lot of, but it is something you should know. This is just another graphical representation. So h is always greater than or equal to g. F is less than or equal to g. So we could use that to help evaluate our limits. So here is what we are going to do. I want to show that this is equal to 0. I have absolutely no limit laws tell me how to deal with trig functions. So I can't just plug it in. It's not even a normal sine graph, sine of 1 over x, so it does some weird things. Now, could we make a table of values or try to come up with a graph? Sure. But the squeeze theorem says, if you want to do this, it's a show, it's like a proof. We're going to prove why this is 0. So let's start with what we know. Sine. If we take the graph of sine, what is the absolute smallest it would ever equal? And the absolute biggest?
1.
1. Okay, so I know that always sine is between -1 and 1. Okay, if this is a proof, you are justifying your reasoning here, so all the steps are required. This isn't something where we can skip steps. All of the examples that I'm going to do are pretty much going to be sines or cosines, and our starting point will be the same because sine and cosine are always between -1 and 1. Does it matter? Do your high and low points change if your angle changes? No. So in order to look like this, I need my angle to be sine of 1 over x. So it would still be true that sine of 1 over x is between -1 and 1. Okay, changes to your angle affect your period, but it doesn't change your amplitude. It doesn't change your high and low points. And so what we're trying to do is turn this expression into in the middle into the one we had up here. So now we have the sine of 1 over x. What am I missing? The x squared. Okay, x squared is positive. So could I just multiply everything by x squared? Multiplying by a positive doesn't change my inequality. So if I did that, if I took all of these things times x squared, then I would get a negative x squared less than or equal to x squared sine of 1 over x less than or equal to a positive x squared. And again, I got that just by taking the previous inequality and multiplying everything by x squared, which is legal because I know x squared is a positive number. All right, so now I have my x squared sine of 1 over x. What's the next piece we need? The limit as it approaches 0. So that's what I'm going to do. I'm going to add that to all the pieces. So we have the limit as x approaches 0, negative x squared, which would have to be less than or equal to the limit as x approaches 0 of x squared sine of 1 over x, which would be less than or equal to limit as x approaches 0 of positive x squared. Okay, I don't know how to do this limit in the middle. But I do know how to do the limits on the end. What would I have to do here? Plug in 0. The opposite of 0 squared is 0. Over here, if I plug it in, I get 0 squared, which is 0. So I have that 0 is less than or equal to this limit, which is less than or equal to 0, which means my limit is in fact 0. Now, if those numbers weren't the same, I wouldn't be able to tell you exactly what the limit was. I might be able to say it's between 1 and 2, if that's what I got for my two limits. But if both of them turn out to be the same number, then we know for certain what that limit was. So that's a little bit different, our first proof that we've really done. Do you guys have questions there?
So you basically just found what's around it without doing a table work. Right?
Exactly. Let's try another one. So, what should my first step be? And that is always your first step. Then we are going to slowly, one step at a time, turn it into this expression. So the first thing I'm going to change is angle. Sine is between -1 and 1 no matter what our angle is. So I can change my angle and make it pi x. Now what would we do? We need to get that x squared. Since x squared is positive, We can just multiply by it. If it were an x, would I be able to do that? No, because we wouldn't know if we flipped our inequalities or not. So I get negative x squared less than or equal to x squared sine of pi x less than or equal to x squared. All right, so now I have all of this stuff. What do we need next?
Is it equal to 0?
So I'm going to add my limit to each piece. Okay, I can't do the limits in the middle, but left and right we can. What's this one turn into?
0.
And this one also turns into 0. So we found the limit as we approach 0 of x squared sine of pi x is in fact equal to 0. Final one? Any questions on that one? Last example. This is a beautiful one, isn't it?
This is a doozy.
It is. Might take us a couple more lines on that one. But where should we start?
Stop.
Sine. I know sine is between negative 1 and 1. Then what do we do? Change our angle. Okay. I've gotten this much. Now what do I do?
Do close.
Um,
Or do the red.
I do the radical first. Order of operations, that's multiplied by the sine. Now, why is it legal to multiply by this radical?
Oh, it has to be.
It has to be positive. If it were a cube root, would I be able to multiply by it? No. But because I know a square root is positive, I can multiply that into everything. So negative 1 times that square root is just my square root. So that's my square root in front of the sine. So now I have all of this. So now what do we need? Plus 1. And we know in inequality it's legal to add the same thing to all pieces. Okay. Nice and long. We have all of this. So now what do we need?
To do that as it approaches 0.
So we just go back and we add a limit. All right, we are almost there. It's a lot. Okay, over here. Do our limit laws allow us to bring that limit under the radical? Yes. So 0 plus 0 squared is 0. Square root of 0 is 0 plus 1. I'm just going to draw an arrow for that. I'm not rewriting that. Okay, over here, if I bring my 0 underneath, I get the square root of 0 plus 1, which is 1. So my limit is equal to 1. So squeeze theorem can help us with some pretty complex expressions. Of course, it's only true in special cases. Like we have to be able to have a function like sine or cosine that is always between certain values for us to evaluate it. All right, any questions? So here is where we're at. You guys have that handout. So you need to finish that first. That is due, today's Wednesday, right? So that's due tomorrow. These book problems are going to be due on Friday. Okay, it's not quite as bad as it looks. So it's under 20. We will either have a quiz Friday or Monday. Okay, and I'm going to let you guys decide based on how this is going. So tomorrow you will have a chunk of the class to work on those book problems. Then I'll also probably do a few review things with you guys. And then we can decide at that point if we feel like we're ready for the quiz Friday or if we need to wait one more day. Okay? So handouts top priority, then you can start your book problem.